Research Center. Before starting with the webinar, a few practicalities for those who are not physically here. I mean, I have like 25 people in front of me, but apart from that, for those who are online, your mic and cameras are turned on by default. So if you have any question, you can type it in the chat, or better still, you can raise your hand and use the icon below. After you raise the hand, it will take me a few seconds to give you the permissions to unmute and turn your camera. Okay. You can switch between two views. I'm the small guy down there in the bottom. So you can click there and you will see me larger. Not very interesting. Or you can see the slides. Okay. So this is the second webinar in this language technology webinar series, which is organized by the HITZ Center, which is a research center called Back Center for Language Technology. We just started with this center 1 year ago. We are more than 60 researchers working on speech and text language technologies, and we are hosted here in San Sebastian in the Basque Country. The webinar today is held together with the Deep Learning for NLP course, which just finishes today. And it's also part of the Language Technologies Master that we hold here in the center. This is, as I said, the second talk in the series. Here you have the link in case you want to check the recordings of the previous talk by Edward Hobby, and also the instructions to, if you want to register for to get news about the next webinars. This will be by Irina Gurevich and Ricardo Baeza. So I just realized that the dates are wrong. So Ricardo Baeza is in February the 11th and Irina Gurevich on March the 4th. Sorry, my mistake. With further ado, I want to present you Kyunghyun Cho. He's an associate professor of computer science and data science at New York University, and he also has the prestigious position of CIFAR Associate Fellow in Canada. So previously he was a research scientist at Facebook Research, a postdoc at the University of Montreal with Joshua Bengio, and his PhD and master studies in Finland. He says that he tries his best to find a balance of machine learning, natural processing, and life. In this picture here, I think we can guess that he manages to find a nice balance in the life side, but also he's very productive in machine learning and natural language processing. He's, I think, well known for his key contributions to neural machine translation and pioneering work on caption generation from images, between other things. Okay, so without further ado, I'll give the floor to Kyunghyun. Sorry, shall I stop my presentation? And okay. Hopefully,
let me see. Oops. Yes. Okay, sure now. Well, thanks for the generous introduction, Neko, and then thanks for the invitation. It's so sad that it has to be online, and then I won't get to be there in person, but hopefully in the future you'll be kind enough to invite me over once more so that I can actually enjoy San Sebastian, again. Can you actually see the slides now on the screen?
No.
Oh.
Not yet.
Oh, I need to click it. Okay, so now I guess you can see the slide.
Coming.
Okay, perfect.
Yeah, no.
All right, there you go. Okay, so today I originally promised to talk about self-supervised manifold-based data augmentation, but then I realized that I gave a talk about this work, but a bit shorter version, a couple of months ago, and then that was recorded, and you can actually watch that talk on YouTube by following the link on the slide. Of course, I'm going to share this slide so that you can actually just click it other than just writing it down. And then I decided that perhaps I need to talk about something slightly different. And I know that this is the end of the winter school on the deep learning for natural language processing. And then I suspect that a lot of you are going to go into the wild and then trying to implement and build a system that is going to be based on deep learning for natural language processing, as well as various other problems that you're going to run into. So I decided that it's probably a better idea if I could actually talk about some of the potential downsides of these algorithms, in particular when they are deployed in practice. Of course, you already have learned about all these algorithms, and then you know all those downsides or the weaknesses, algorithmic weaknesses. However, when you start deploying these algorithms, even the strength of these algorithms or the algorithmic strength can in fact become the issues that we couldn't easily expect in advance. So today I'm going to talk about the unreasonably shallow deep learning. That is that although the algorithms are very deep, our models are very deep, but how they behave could very well be shallow. In particular, I'm going to talk about the three, let's say, aspects that I find very shallow in our current practice of deep learning. That they are non-identifiability, spurious correlations arising from confounders, and the feedback loops in machine learning. And I'm going to try to describe each one of them carefully, and then trying to give a set of possible technical solutions to that. But also, I'm going to talk about how the existing technology cannot really address any one of these perfectly. And then I'll try to finish this talk by talking about what we can do in order to minimize any negative consequences of these systems. All right. So first, non-identifiability in deep learning. Now, this non-identifiability implies that when we start with our deep neural network and then we train a model to solve a problem, we actually never end up finding the correct solution. That is, there is always an ambiguity in the solutions that we get from training these deep neural networks on a finite amount of data. Another way to put it is that there are so many seemingly perfect solutions exist with finite data and feature dependencies, and then often it's very difficult from the algorithmic point of view to distinguish across all those different seemingly perfect solutions. These things happen like everywhere you can imagine. When you build an image caption generation system, when you build an object recognition system, when you build a question answering system, you're going to end up with many amazing solutions that look from the parameter space point of view very, very different from each other. However, when you look at the validation loss or the validation accuracy, they look essentially same. However, it turned out that they are indeed different. Let me see, yes. And then what do we mean by this, the ambiguity or the different solutions, and then the fact that they are different? Let's think about this very imaginary, let's say, mental exercise. Let's run some the mental exercise here. Let's say we want to build a bird detector. And then we're given these 4 training examples that I collected from the Google image search by just typing birds. And then, of course, the goal of this bird detector is to tell if there is a bird or not in the image. And then, of course, there are so many perfect solutions given these 4 examples. I can build a bird detector that's going to look at a branch. And if there is a branch in the image, then this detector may simply say that there is a bird. And then according to these training instances, that's a perfect solution. Another solution is to build a detector that's going to detect a beak. And then if there is a beak in this image, then it's going to simply say that there is a bird. And then again, this is one of the possible perfect solutions according to these 4 training instances. And then the funny thing is that it's not overfitting. So I'm not talking about overfitting, because if I look at more images that I collect by doing the same kind of Google image search, we notice that both of these solutions do work pretty much perfectly on the images that are not training instances. Whenever I have a picture of a bird, it's almost always that I'm going to see the beak of the particular bird, meaning that my bird detector is going to work really, really well. And then what is the chance that I would ever get an image with a beak but not a bird? And similarly with the branch, if I go into the wild, that is the Google image search, and then trying to find all those images, and then when I look at all those images, and then if I see an image with a bird, it's almost inevitable that I'm going to see a branch on which that bird sits. What that means is that both of these detectors are going to, in fact, weirdly generalize very well as well, although they are very different detectors, and then we already know that which one is better than the other. And then the funny thing is that this doesn't really happen only with these toy examples. So Emily Denton, who graduated from NYU as a PhD student in 2018, who is now at Google, has written a very nice paper analyzing the smile detection problem. That is that if you build a deep neural network that's going to take as an input an image of the person's face, let's say front-facing face, and then if you train it to detect whether the person is smile or not, then what does it actually use in order to tell whether the person is smiling? It turned out that this deep neural network uses a lot of weird features that we as humans do not think are relevant, nor in fact correct. For instance, according to her analysis, higher cheekbones make the probability of smiling lower. But we know that having higher cheekbones have nothing to do with whether the person is actually smiling or not. And then there was a feature that makes the deep neural net was relying on the feature of the size of the nose. And then it was saying that the bigger noses make the probability of smiling lower. And obviously, I mean, perhaps unsurprisingly, that this deep neural net became an age detector, and then simply said that if the person in an image looks younger, then the person is more likely to be smiling. And furthermore, these, let's say, undesirable or the unexpected behaviors often manifest themselves in a very subtle manner. So this is a paper from Facebook AI Research in 2019 that was presented at a workshop in the CVPR that year. And then there, what they did was to took a look at, they investigated all the available off-the-shelf commercial object recognition system from Microsoft, object recognition system from Google, object recognition system from any other company that you can imagine that you can actually go use nowadays if you want immediately by just sending out the credit card numbers, and then you're going to have access to all those state-of-the-art object recognition system. And then what they realized is that the accuracies of those commercial off-the-shelf object detection systems, which almost inevitably rely on deep learning, depend on the income level of the place where the picture was taken. So if you give the picture of that was taken in a high-income country or the cities, the object recognition system is more likely to work better. On the other hand, if you take pictures from a low-income cities or the household, then the object recognition system suddenly drops its accuracy. And then what that means is that somehow this object recognition system is using a feature that is somehow correlated with the income level, and then use that information in order to make a prediction, not based on actual objects that are present in an image. And then one of the conjectures that they had in the paper was that the discrepancy between where the training instances were collected. So for instance, if you look at images from ImageNet data, you do notice that most of the images were collected from either North America or in Europe. However, if you look at the world population and then where the actual test images are often taken, they are from, let's say, China, Africa, and India, as well as North America and Europe. What it means is that there is this discrepancy, and then because our deep neural networks do find all these weird features and still are seemingly perfect, in the test time, when the deployment time, these neural nets are going to behave in a way that is very unexpected. And then the funny thing is that it's actually not just data, but also algorithms. The apparent success of all these solutions, so given one deep neural network and given one data set, we get multiple solutions. And then when we test it at the lab on our computer using a fixed finite size validation set, they all look seemingly perfect. And then that creates a false illusion that the algorithm is perfect. It's not the fault of the algorithm. And we tend to put too much blame on the data and too little blame on the algorithm. But it turned out that that's not necessarily true. Our algorithms are, imperfect as well. And then, that's the thing that I'm going to talk about further throughout the rest of my talk. And then in order to think about this, it's a really nice way. The Gebru et al. Last year put out a technical report with this idea of the taxonomy of decision rules, where each decision rule corresponds to each parameter configuration of a neural network. Now, you can think of this as a very big set or the infinitely large space. And then what we notice is that most of the deep neural nets are useless, so we don't really care about it. But by solving the problem of learning, that is the optimization, we actually end up with a lot of solutions that solve the training instances perfectly. Those are the overfitted solutions. And among those solutions, we have a small subset that generalizes really well according to our finite size validation set. And then they call it shortcut solutions. And within these shortcut solutions, there is the intended solution. And then the intended solution, which is a very small subset of this infinitely large decision rule space, that's the place where the deep neural network that we have trained, in fact, solves a problem in a way that we know is correct. That is, this smile detector should not just guess that the person is smiling because the person looks younger. So we have that intended solution, but this intended solution is really small. And then given only a finite size validation set, we cannot really tell the difference between those shortcut connections that are not intended solutions from the intended solutions. And then the funny thing is that it actually happens in practice. So this is a result from the Weber et al. From 2018. They in fact used the, if I remember correctly, attention-based recurrent neural network, which I believe you have learned from this Wiener school. And then they created some synthetic data to train this model. And then when doing so, they also created a set of so-called out-of-distribution test sets. So the standard test set has sequences of all the properties that are very similar to the sequences from the training set. On the other hand, repeat, short, and long, these specialized test sets do have the sequences that exhibit very particular properties. So for instance, in the repeat data set, there are a lot of repetitions within the sequence, unlike the sequences from the training set. And in the case of the long test set, most of the sequences are longer than the sequences in the training set. And the funny thing is that they trained it multiple times by varying the random set, and then ended up with a number of solutions that are just equally good in terms of the standard validation set. However, when they tested each and every one of those solutions on these out-of-domain or the out-of-distribution test sets, what they ended up observing was that each and every one of these solutions is different from the other. So for instance, the one from the one in the bottom of this table, that solution works really, really well for very short sequences. However, it almost completely fails in the longer sequences. Now, on the other hand, if you look at the third solution that was trained with a random set 10,000, we see that it works almost perfectly on sequences within many repetitions, but it really, it completely fails. It never managed to solve long sequences well or correctly. So what that means is that it really happens, and that a lot of, let's say, models that you have trained following the during the lab sessions of the Wiener School, I have looked at some of them, will have this kind of property. If you retrain it with a different random set, you're going to end up with a very similar looking model that works equally well on the validation or the test that you have used. However, when you start looking into more corner cases, you're going to notice that those two solutions behave very differently from each other. Now, how can we actually avoid this issue? One kind of, let's say, band-aid solution is to be Bayesian. That is that we try to frame this non-complex optimization problem that we need to solve in order to train deep neural networks into a Bayesian posterior inference problem. I'm not going to go into a detail, but I'll share the slide so that you can go into detail and then you'll follow through on that. And in this view, what it tells us is that instead of, let's try to see if the pointer works. Hopefully pointer works, right? Instead, so you can imagine this as a hypothetical view or the simplified view of the non-convex optimization function or objective function that we try to minimize when we train the deep neural network, or the maximize in this particular case. And then you have this Bayesian approach tells us that we should look at it from the distribution point of view, and then try to look at all the solutions in this solution space. And then after considering all these solutions that are very likely or that are very good, what we do is that we're going to average the predictions from all these reasonable solutions. And then by doing so, this actually allows us to avoid any individual solution's idiosyncrasy to some degree. Of course, it's impossible to remove all those idiosyncrasies perfectly due to many reasons, including the computational feasibility, as well as the lack of, let's say, very efficient and effective Bayesian sampling algorithms. So it's not perfect. However, it does help us in some sense. And then I'm not sure if you have learned in the lab sessions and during the winter school, and this is one of the things that we always do in practice as well. If you want to get the squeeze out that last mile in the accuracy, as well as to reduce the variance in the prediction, that is to make an ensemble of many different solutions. However, it turned out that it's actually not perfect, because observations alone cannot remove those weird spurious correlations, where the spurious correlations refer to correlations that are not the correct or the true causal correlations. So at this point, I want to throw you a list of questions that I think you should always think about before thinking about solving a problem with your deep learning algorithm, and also especially before you decided to deploy such a system that you have built using these machine learning algorithms. And this question, the gist of these questions is that how can we tell whether my AI system or the deep learning based system work well? It turned out to be a surprisingly difficult question. So then this actually question with how we can tell our system works well, and if the answer is no, or as in it doesn't work well, then how can we actually address it? And that leads to the question of causality versus correlation. It's very fascinating topic. I have to tell you, I'm very far away from being expert in this causality versus correlation issue. In fact, I'm probably going to say a lot of wrong things during the next, let's say, 15 minutes or so. But it's a very interesting to think about. And this actually does reveal, even the high-level discussion does reveal some of the core weaknesses that we have in our deep learning approaches. So one aspect, or the one potential cause behind these undesirable solutions, the shortcut solutions that are not intended solutions, is the existence of so-called unobserved confounding factors. So when we imagine how our data, let's imagine a supervised learning data, how our data appears or was generated, we often think only about what we observe, that is that the X and Y. And then we're going to assume that the either X was caused by Y, or the creative generated from Y, or the other way around. However, in reality, what happens is that we know that we don't observe the entire world perfectly, but that means that we have the process that includes something called confounding factor that influences both the X and Y. And then these confounding factors are almost always unobserved. We try our best to observe as many confounding factors as possible, but it's just impossible, simply impossible to observe all of them, because we often don't even know what those confounding factors are to start with. And then this is the reason why we always hear this, the very wise words, correlation does not imply causality or the causation, right? So let's think about, let's go back to the example of the bird detector. And then, we can imagine either direction. That is that the category bird, so Y causes the display of an actual realization of a bird, or the visual perception of the bird causes our brain to recognize what we see as the category birds. But directionality in this case doesn't really matter for our, let's say, purpose of our discussion. But in either of these cases, we know that there exists a hidden confounder. And then what is the hidden confounder here is the location at which the picture was taken. And then in the case of the birds, we know that if the location was forest, then it's very likely that the birds are going to be present. And then that's going to influence both the picture that we take as well as the category that it is. And then what it means is that instead of the true causal vector path that is going from the x to y directly, that is that, okay, here's a image of a bird, and then that causes my brain to think that there is a bird. But in addition to that, there is another path that goes through this confounding factor, hidden confounding factor, that is the location. And then what happens is that if we do not have this explicit observation of z, then we cannot really tell what this true confounding factor is. That's due to this inequality, this identity, that is that the p of y given do operator on applied on x is only equal to p of y given x, that is after marginalizing out this compounding factor under a certain condition that is almost never satisfied. So then, of course, we want to observe everything, but we cannot observe them. And then one of the things that people have been doing, let's say in economics as well as the medicine and so on, in order to avoid this issue of the unobserved confounding factor, is to run randomized control trial. Now, nowadays, everyone is expert in randomized control trial due to the RCT that is being used for developing a vaccine and then testing the efficiency as well as the efficacy of the vaccine for COVID-19. But the idea is very simple. If we could replace or intervene and then set the value of x to anything that is drawn independent of the actual value of the unobserved confounding factor z, then we suddenly are able to break this link that goes from z to x. And then that allows us to measure the true causal effect of x on y, that is the effect. Unfortunately, it's not easy. So because when you don't know the confounding factor z, then it's difficult to tell what is the right way to get x that is going to be independent of z. How do we know that whatever we have done is independent of z? When the dimensionality is really, really low, as in, let's say, vaccination, that is that, okay, so we give the vaccine or not, or whether it's a vaccine or not. In that case, we can think about the very uninformative distribution from which we sample, and then that's where the randomized control trial comes in. However, in this kind of high dimensional space in which we work, that's very difficult. Even defining a uniform distribution over this kind of high dimensional space is very, very difficult. And that's one thing that I'm working on at the moment for ICML, whose deadline is next week. So then, what we want is that we probably want to combine or bring in the expertise of humans into this machine learning system. And then that's how we end up with the concept of human and model in the loop. And the motivation behind this human and model in the loop system is that somehow humans, we know those, like the hidden or the unintended path. How do I know that we know? Because, as we have just talked about all together, we actually were able to figure out that our bird detector is not a good detector if it was just detecting a branch. We somehow knew. So then can we actually use the help of us in order to make machines ignore those unintended paths that connects the x and y via unobserved confounding factors? It turned out that yes, we can for many problems that we think are very important and where deep learning systems can work well. So this is a work from Facebook AI Research from 2019 and 2020. And then they built the so-called adversarial natural language inference data set out of this, is that they asked the humans to figure out or create a new example that is similar to the existing examples, however, is going to fool the system that was trained on the existing examples. So that is, we're trying to provide a counterfactual example that's going to flip the decision of the machine learning model that has been created. And then it turned out that the people are amazingly good at this. It's quite surprising, but they were able to interact with the system just a few times, and they were able to come up with a lot of these meaningful counterfactual or adversarial examples. Furthermore, this was also done by the Koshik et al. From CMU in the same year. And then here, sometimes you can even create all these adversarial examples without necessarily having access to the labels from the models. And also they show that these adversarial examples are transferable from one model to another, and often going beyond across the boundaries of the model classes as well. So, and then the very interesting thing is that it can actually help us identify what kind of spurious correlations our models are exploiting incorrectly in order to solve the problem. And also, of course, knowing that can almost always help us build a better system, even if that is not trivial. But it turned out that this is not necessarily the best way forward. It is a better way forward than what we're doing at the moment, that is having a fixed validation set. However, this is not the optimal way to go because it becomes increasingly more difficult. As we retrain a model on a collected data set, the data set that consists of the data points that were collected to be adversarial or counterfactual by humans inspecting the model gets better. But as the model gets better and better, it becomes more and more challenging for humans to figure out what are those counterfactual examples. We are good at it. Unfortunately, we are not perfect at it. And then in fact, using this kind of system in practice, that is in the deployment scenario, can be very dangerous because in this process, humans, we may actually suffer from the process. I highly recommend you to take a look at this article titled "The Trauma Floor" by Casey Newton, where the journalist went talked to people, interviewed a lot of so-called human content moderators of Facebook, and then they noticed that a lot of those human moderators, after working at this, let's say, moderation center, I think in Arizona for half a year to a couple of years, they do suffer very severely from the mental trauma. And then what we are effectively doing is to do the same thing with a machine learning system in the loop. So what that means is that this kind of, let's say, mental trauma will still continue to happen with the humans. And then we don't want to really sacrifice us in order to make our machine learning system better. And then unfortunately, even more so, these human and model in the loop, when it's put into the deployment scenario, often end up hurting disadvantaged populations disproportionately more. So, for instance, let's say Zoom is a tweet from last year. So when you use Zoom and then use the background feature, it turned out that in a lot of cases, the face of the Black person disappears because the Zoom detects that there must be some kind of artifact or the noise. And then of course, because we know that, I'm pretty sure Zoom will be able to this issue by collecting more data and then retrain their model so that their model is not going to say that the Black person's head is a noise. However, until that happens, this is the Black population that's going to suffer more than the other population. So it really does negatively impact the disadvantaged populations more, and then we want to minimize this kind of negative consequences. And similar thing between male and female. This is another example from about 3 years ago. Whenever the picture of a person is uploaded, or at least back then uploaded to the Twitter, what often happens is that if it's a male person in the picture, the face is going to be centered or the cropped in. On the other hand, if it were female speakers or the female in the picture, then often the breast area is going to be cropped in and centered, which is a pretty horrible thing to do. But one of the things that was revealed later on was that the one data set, one particular signal that the Twitter used in order to build this kind of system was the gaze data that was collected. And then who do you think, we can guess who were those people who participated creating the data. It was a male grad or the undergrad student. So we can see that this one does hurt again the disadvantaged population, in particular for many of the, let's say, managerial or the executive roles, because there the women tend to be minority. So often this kind of early deployment and iterative refinement is not an option, and we have to really be careful. And then even worse, this kind of thing often leaves irreversible damages as well. You have learned about the natural language processing, and you have learned about the machine translation. And I never thought that the machine translation would become good enough or actually bad enough to hurt people, but it turned out that the machine translation does end up hurting people. So this is one particular example from 2017. The BBC reported that the Israeli police arrested a Palestinian man based on the mistranslated post on Facebook. And then this is who knew? I mean, I didn't know, certainly, but this kind of thing happens. And then what happened to this Palestinian man is not reversible. This person must have gone through a huge, let's say, ordeal, and then must have ended up with a huge mental trauma. And then that one we cannot really reverse it. So we have to be really careful when we're trying to deploy this kind of human model in the loop. And there are so many such examples, and then those examples only are accumulating over these days, because we are increasingly deploying more and more machine learning based systems. So if you want, I highly recommend you to take a look at these books and articles that are linked in this slide. I'm going to share with you in the future. And then one of the issues, even if we can, let's say if we are working with a very benign application so that we can work with the human and machine in the loop systems, or the kind of, let's say, scenario, it's still difficult because it's very difficult to come up with the causal graphs themselves. So for instance, when we have, let's say, 3 or 4 variables, then of course we can come up with the causal graph based on our understanding of how the world works. In the case of, let's say, vaccination, we're going to simplify it so much that there's a one treatment that is the vaccinated or not, and then there's going to be one effect that is going to be whether the person is going to be infected with coronavirus or not. However, in reality, in particular, the problems that we want to solve as a machine learning people is often impossible. Let's say I want to think about this bird detection example. There are millions of variables because every single pixel could be considered as a random variable. And then now I need to figure out what is the right causal graph behind this extremely high dimensional, or this system with extremely many random variables. We simply cannot do that. And that has been noticed by a lot of researchers in machine learning field who were getting more and more interested, and then we are in general getting more and more interested in the causal machine learning. So then there is one potential idea that can save us from having to come up with a causal graph or the theory behind, let's say, pixels of images or anything like that. And then there is the principle of the invariance, or the principle of invariance to environments. That is, intended solutions, so those good solutions, are often invariant to environmental changes. That is, if I build a object detection system that works on this Earth, then I expect that object detection system works equally well in Mars, for instance. So for instance, if I have a face detection system, of course, human face detection system should work regardless of whether we are using that in the space or in the Earth or under the water. And then we can use this invariance principle in order to build or trying to identify an intended solution. So in the case of the bird classifier, we know that the second classifier that looks at a beak of the bird is better, because that one is going to work well even when we are that detector is presented with all those images of birds in the cage or indoors where there was no branches. So then what that means is that perhaps we can use this in order to train our classifier to be invariant. And then that is the idea of the invariance principle that was put forward initially by the Peters et al. In 2015. So in the case of the bird detector, what I'm going to do is I'm going to create two different environments. One environment is where the location, that is the confounding factor, was forest, and the other environment is the where the location was permanent. Of course, I don't really need to know all those confounding factors as long as I can vary or diversify the environments as much as I can. And then what I do is that I'm going to build a classifier that's going to work well on all these environments. And then this somehow works as if we're intervening on the unobserved confounding factors. And then this actually ends up with the idea of the so-called invariant risk minimization. That is, we want our representation of this deep neural network or the classifier to be invariant to the changes in the environment. And then this is highly connected to the so-called bi-level optimization, because we'll have to solve the optimization in two different levels. Inside, so that is in the inner loop, we need to train a model that's going to work for a one particular environment, but then there is the outer loop that's going to go through all those environments so that the resulting classifier is going to work well across all those environments. And this is very much connected to so-called meta-learning, and then which is one of the hottest topics in machine learning as well as the natural language processing these days, where we're trying to find a representation that's going to be good for all possible different problems that we will need to solve in the future. So we want to solve the problem of the multitask learning, but we assume that those multiple tasks are not necessarily available in incomplete in advance. So what we want to do is that we want to use a small subset of the tasks that are available in the test training time in order to get a representation that's going to be invariant to the particular choice of the task that for which this representation is going to be used. And furthermore, it turned out that based on this idea, it turned out that we now get the sense of why data augmentation is important and data augmentation works well. And then in particular for the low resource language, natural language processing, data augmentation can be very useful. And then yet it turned out that what this data augmentation does is to very cheaply mimic this process of the invariant risk minimization. So in the case, let's take as an example of this bird detection problem. And then what we notice is that the branch on which the bird sits is almost always at the bottom of an image. Do the data augmentation by shifting or translating or cropping, then it's possible that most of the times this branch is going to disappear. On the other hand, the bird is in the center so that the classifier only looks at the actual bird over and over without having to look at the branch. And then that actually helps. And then what that means is that the data augmentation could be viewed from the perspective of creating all these environments on the fly. It's very much limited intervention or the limited way of intervening on the data generating process. However, this may be one way to explain the effectiveness of the data augmentation. And then when you build a natural language processing system, you can imagine viewing the data augmentation from this angle and then trying to come up with a good, let's say, good and cheap way to generate all those data in order to make a more robust or invariant classifier or the system. So we just talked about the invariant risk minimization, but again, still quite limited. It's a very nice way forward, but it's very limited in a sense that we need to really have all those, let's say, different environments. In the natural language processing, you can think about having all those different domains. So you might want to have a classifier that's going to work on the Amazon reviews as well as, let's say, IMDb reviews. But it sounds pretty obvious, but then you notice that, oh, how do we even define these domains? How do we collect all those data from all these different domains? And then how do we even know that the data that I have collected contains all those diverse set of domains? So it's quite difficult problem, but it looks like a very nice first step toward trying to build a practical algorithm that's going to result in a invariant predictors. So it turned out that the existing algorithms and practices are limited and cannot really solve this problem of artificial intelligence or building a deployable and generalizable machine learning system. It can do, and then our technology does allow us to do it to a certain level, but it's going to take much more advances in algorithm in order for us to build a really, really satisfying system. And then a bit of a high-level analysis from the causality perspective tells us that we need some kind of intervention, we need some kind of invariance, then we know how to do them, each of them, little by little, but not enough. But what this means is that this is a really nice direction for future research. Now, the final topic, feedback loop in machine learning. This one is so much more practical than before. So in the lab, what we do is that we collect data once, and then use that data for testing or for training a model, and then we evaluate it, and then we often go back and forth between learning and evaluation stage. And then rarely we look at the evaluation and then we change the data collection procedure, we collect the data again. However, in reality, there is one more step at the end, that is the deployment. And the funny thing is, deployment actually implicitly affects the data collection procedure. And then that actually creates a weird feedback loop in machine learning. And I'm going to look at quickly two scenarios. One is data contamination and two is exploration versus exploitation. Now, let me actually skip this vision part, but let's go to the machine translation, which is more relevant to the winner schools content. That is a deep learning for natural language processing. So unfortunately, this GIF doesn't work, but you can actually search for this GIF very easily on Google by searching for Google Translate, the improvements over time machine translation. And then what this GIF was supposed to show is that in 2007, the y-axis is the quality of the machine translation system, and then x-axis is all the languages that they serve, and then they are sorted according to the size of the data that they have. So this is what happened. This is what happened in 2007. But now, if you play the GIF, if I were able to play the GIF, we notice that we actually get to this level. So the Google Translate, by using this neural machine translation, has improved a lot over the past 10 to 13 years. And then this improvement is not only on a data-heavy languages, but also on very low resource languages as well. So this is great. But the funny thing is, this actually creates a problem because often the best way or the very effective way to collect large amount of parallel data in order to train this machine translation system, especially in the places like Google, is to mine these parallel corpuses automatically from a vast amount of knowledge on the web. So they're going to go through all the pages in the web, look at many of those news articles, Wikipedia, e-commerce sites, and so on, in order to find if there is a translated pairs of documents, and then use that in order to create a data for building a machine translation system. However, increasingly, people use Google Translate to translate their own content, and then use that to create all those pages in different languages. And this is increasingly so because Google Translate has become so much better. And what that means is that there's a weird feedback loop. So Google built their own data by scraping web, and then they built the amazing Google translation system using that data, and then they made it usable by both the paid as well as the free tier users. And then they're going to use that system to create all those content on the web that's going to be, again, used in the next iteration by Google to create the data that's going to train the Google Translate system. Means there's a vicious cycle, and then the quality is going to degrade over time because of the consequence of the garbage in, garbage out. So of course there are some solutions. So for instance, there is something called statistical watermarking. So if you remember from some time ago or many years ago, when you watch the movie, let's say on a plane, when we used to fly, there's always a watermark of which airline you're flying, so that even if that is hacked and then you have to release publicly, they can actually down where the hack or the leak happened. Now we can now do that without showing you the actual watermark by being statistical and algorithmic. So we can create a translation or the biased translate system in a way that's going to make a mark that is invisible to us, but statistically is visible to the algorithm that is collecting the data from the web. So this kind of thing happens. Unfortunately, it turned out that there is a trade-off. That is that if we apply the statistical watermarking to be very, very exact, so that we can always tell whether the given text was Google translated or not, the quality of the translation itself drops. So we need to make a balance between these, which is very not ideal. And then, of course, furthermore, what this means is that the use of this statistical watermarking is going to allow these big companies as well as the governments to be able to track who wrote what and who read what. Right? What is the degree to which we're going to tolerate that is a big question that we need to answer before we deploy this kind of approaches en masse in order to avoid this issue of the feedback loop. So this is really a difficult problem. Now, the second thing I want to quickly touch upon is the personalized feed. And then this one, I'm not going to talk about it too much, but you go to the Google News now on your laptop and then compare it against your peers or your family members, and you're going to notice that everyone sees different headlines or the different, let's say, top news. For instance, the three screenshots I made at the same time, one on my laptop, another one from my girlfriend's laptop who was sitting in the same room, and then the third one, it was made from my friend's laptop who was sitting in the same country but in different state. And then what we see is that they do look very, very different. And then in particular, when we look at more of the personalized version, according to Google News, the difference was very stark. And then of course you can guess, which one was mine, because I always talk about AI and so on. So Google News already knows that I'm going to be interested in AI. But then there comes a question. Am I interested in AI because I'm intrinsically or inherently interested in AI? Or is it because Google News tends to show me all those AI related news and articles so that my interest in AI is amplified? So there is the issue with so-called filter bubble and so on. And then it turned out that the predominant paradigm of supervised learning completely fall into this issue of the feedback loop, and then cannot be helped. And then we have to go into other alternatives such as the contextual bandit or whatnot that has the component of so-called exploration. That is that this algorithm is going to try something that is not supposed to be good in order to figure out if there is a better solution. And then this one needs to solve this dilemma between exploration and exploitation, because every time it explores, there's a chance that it's going to actually perform really, really worse than exploiting what it knows. However, this is a good practice, except that it's become very difficult to deploy in this kind of large scale setup where billions of the people are using these recommendation systems. And then every recommendation system is working with billions of articles. So it's a crazy complicated recommendation system that needs to work in real time across the globe while the users change as well as the articles change. What that means is that if we have to somehow be parallel, and then that's what all this social media does. They all have the users that are in the order of billions now, hundreds of millions to billions nowadays. And then in fact, they need to run experiments that is in the name of the exploration. And then there is a big question. We know that in this kind of massive scale, if we run the experiments in parallel, we can tell what is going to be really good for users or whatever the objective function you choose to do. However, what kind of experiments are allowed and then should allow ourselves to run? In 2014, there was a very controversial paper that was published from Facebook where they actually kind of revealed that they ran an experiments on the real Facebook users without explicit consent by changing the amount of emotional contents being presented on each of the users that was arbitrarily controlled. So some users saw a more positive post more, some other users saw more negative post, while the remaining users saw a very neutral post only for many weeks. And then what happened is that they noticed that the emotion is contagious, and also there's a withdrawal effect. That is that the people exposed to fewer emotional posts were less expressive, meaning that they interacted less with other people on Facebook platform. And then you just, start asking yourself, I think that this is a good question to ask yourself. Hypothetically, if you are a decision maker at Facebook and then you saw this report, what kind of decision would you have chosen when the company's bottom line is highly related, if not is perfectly correlated with the level of engagement users have on Facebook platform? And then this was a kind of the same thing that brought up a lot of questions about what kind of experimentation or what kind of exploration should be allowed in order for us to build a machine learning system that can break free of this kind of feedback loop. There is no consensus on what is the right thing to do, but as a machine learning practitioners, we all have to think about this very, very carefully whenever we try to design a system that is going to be deployed in the wild. Now, the final thing that I want to talk about in this feedback loop issue is that there are cases where we cannot use statistical watermark, we cannot explore, nor we cannot run the massive parallel experiment. And one such example is hiring. We cannot experiment with people's career and life, so we cannot really do random assignment or anything like that. We cannot statistically watermark people, that's impossible. And then it only happens once. You make a call for hiring some people, you hire them, you hire some, you don't hire the others, and then that's the decision they made, and then you cannot repeat this over and over. So in this kind of scenario, what is the right way to do? Should we even use machine learning algorithms? If so, what is the portion that we are going to allow ourselves to use machine learning in this big process of hiring or this kind of irreversible process? It's a very interesting thing that you might want to think about. And then this kind of thing also is the thing that the companies have tried, and then fortunately, at least publicly, they have decided to stop. And then the company was Amazon in 2018 or so. So the thing to think about is that whenever we build this kind of machine learning based systems and then deploy it, that creates a feedback loop between society and artificial intelligence system. And because these AI systems are not static, they are going to both influence the society, but also will be influenced by the society that it influences itself. And then we want to make sure that this cycle is virtuous, not vicious. And there are many different ways to approach it technically, but a lot of the algorithms still have the issues of the scalability as well as some of the ethical considerations that need to be made. Now, so the concluding words, I think I'm almost perfectly on time. First thing is that whenever you build this kind of system, you really need to get the data yourself and make sure that you are using the data that you thought you are using. And then one of the things that exercise that I like to do, and then I like to do with my students, is to look at the paper by Gebru that is the Datasheets for Datasets, and then try to see if I'm able to answer the questions that this paper recommend, or the kind of tells us that we have to be able to the answer in order for us to use that data set for any kind of production system. And then it's actually not easy. So you've been using all those data sets during the lab session in order to build all those machine translation systems and so on. But go look at these 7 questions, then trying to see how many questions you can actually answer. And then you notice that it's very difficult to answer these questions, even one of them. For instance, if you use the data from WMT in order to train your machine translation system, can you answer the first question? That is who created the data set and how can they be contacted? I'm pretty sure almost none of you, including myself, can answer this question fully. So it's really important to know about your own data. And then the second thing is that you need to know about the model that you have created. And then this one, I suggest you to look into the Michel 2018 about the model cards for model reporting. And then in this particular case, we're not asking about the data, we're asking about the models. And then we're asking about how these models are going to behave in scenarios that are not necessarily common. And then again, you notice that a lot of times we actually don't know the answers to these questions, and then we have to run experiments in order to answer these questions and deploy this model card together with the actual models that you deploy. And then the final thing that I want to talk about is that we need to be able to imagine the consequences of our model due to the because this is because of the potential value misalignment. It's possible that even if we did everything right, things are going to go wrong. So for instance, Instagram or any kind of social media, the goal, like the mindset there is that, okay, if the users are more engaging, and then they're going to, and that leads to a more social interaction among them, and then more social interaction among the friends or the family definitely makes them happier, and then more happier people on the society, that makes the society better. So thereby, the goal of social media should be to maximize the growth of the user base, because you want to have many users who are going to interact with each other, and then increase the engagement level of users. It kind of sounds okay logic, not perfect, okay logic. And then in fact, funny thing is that the social media companies have been very successful at this goal of maximizing the growth and engagement. If you look at the Instagram, from the Instagram homepage, the total number of monthly active Instagram users is over 8 billion, and number of photos and videos uploaded per day is over 100 million. So they are very successful at achieving this goal. So they've done everything right. However, it turned out that the Instagram, one of the worst social media, in a sense that the users are actually less happy by using Instagram and interacting with the people on Instagram. So what that means is that the alignment of the value completely failed, and then this, I suspect that is maybe due to the lack of the imagination. So when we build our system, we need to be able to imagine various scenarios in which our system is going to be used, and then in particular, we have to make sure that we are able to imagine not only the happy scenarios, but also the negative scenarios that's going to have a very negative consequences. So truly the final slide. This is a paper that I just read recently by Channel, titled Ethical Machine Learning in Healthcare, although they actually are focusing on healthcare domain. However, the 5 recommendations that they make are in fact applicable to machine learning in any domain when we think about applying this. Let's just go through them one at a time quickly. The first one is that we really should make sure that we are going to be a diverse team, so that we can look at what kind of outcomes are going to happen when we deploy this system. So this is connected to the imagining the consequences, and the consequences should be about the whole diverse or the entire spectrum of the people who are going to use or be impacted by it. Second one is that we have to really think about the data collection very, very carefully. As we saw in the very beginning with the example of the bird detectors, if you're not careful, you are going to build a branch detector instead of the bird detector, but fool ourselves that our branch detector is a bird detector. 3, we have to think about how unbiased the outcome choice is going to be. Kind of obvious things, but it's very difficult to exercise. The 4th recommendation is that we have to have goals in our mind in advance, so that we actually know what we are doing all the way throughout this whole process. And final recommendation is to have the system of the auditing. So over and over, we need to be able to identify the potential harms or the negative consequences, and be able to identify them and fix them in the system over and over. And then that's going to be can be done by the occasional auditing. And that actually concludes my talk. I'm sorry I went over 4 minutes, but there was the introduction at the beginning, so I'll say I hit the exactly 1 hour mark. If you have any questions, I'll be happy to actually stay here for another 10 to 15 minutes to get any questions. I'll share the slides, and if you have any questions, of course, further, you can email me. I cannot promise the immediate reply, but I can always try to do so. So actually, there are seems like a question on the chat window. So
yeah, thank you, Kyunghyun. Jan, I wanted to
yes.
give a round of applause first.
Thank you very much. Yes.